కాలేజ్ ఆఫ్ ఇంజనీరింగ్ అండ్ టెక్నాలజీ 2008 లో స్థాపించిన కళాశాలలో MBA, NAC A గ్రేడ్ మరియు ISO సర్టిఫికేషన్ సాధించిన మొట్టమొదటి కళాశాల శ్రీ ముత్తవరపు వెంకటేశ్వరరావు కాలేజ్ ఆఫ్ ఇంజనీరింగ్ అండ్ టెక్నాలజీ త్వరలో అటానమస్ కాబోతోంది. 2014లో ISO గుర్తింపు, 2015లో రాష్ట్ర ప్రభుత్వంచే A గ్రేడ్, 2016లో NAC A గ్రేడ్, ఇప్పుడు NBA సాధించిన సంస్థ శ్రీ ముత్తవరపు వెంకటేశ్వరరావు కాలేజ్ ఆఫ్ ఇంజనీరింగ్ అండ్ టెక్నాలజీ.
Good morning. So in the last classes we discussed about all these topics. Yes. Okay. In the last classes we discussed about the Fourier series representation of continuous time periodic signals, properties of Fourier series, Dirichlet conditions, trigonometric Fourier series, and exponential Fourier series. Okay. Next, relation between trigonometric and exponential Fourier series, complex Fourier spectrum, deriving Fourier transform from Fourier series. Next, Fourier transform of arbitrary signal. Next, Fourier transform of standard signals. Next, Fourier transform of periodic signals, and the properties of Fourier transforms. Fourier transforms involving impulse function and signum function. Right? So all these topics we discussed in our earlier classes. Let us we see the overall view of the second unit. Okay. So see, Fourier analysis is a powerful tool. It is a useful tool for analyzing or representing the signal as well as system performance analyzation in frequency domain. So here the signal characteristics can be represented in terms of amplitude spectrum as well as phase spectrum. What is meant by amplitude spectrum? We will draw the graph between amplitude versus frequency. Similarly, phase spectrum means we will draw the graph between phase angle versus frequency. Next, frequency domain analysis is of systems provides many advantages over time domain analysis of systems. Like convolution in time domain becomes simple multiplication in frequency domain, right? Convolution in time domain becomes simple multiplication in frequency domain. Next, here we have two types of or two forms of Fourier series are there. First one is trigonometric form and second one is exponential form, right? Trigonometric form and exponential form. So trigonometric form, if we take the trigonometric form, here the arbitrary signal m of t can be represented as m of t equal to m of t plus t naught, where t naught is the fundamental time period, and f naught is the reciprocal of the fundamental time period, that is fundamental frequency, f naught equal to 1 by t naught, right? F naught equal to 1 by t naught, right? So m of t can be represented as a combination of DC component as well as harmonic components, or these are also called as sinusoids of fundamental frequency f naught, and its higher harmonics f naught, 2f naught, 3f naught, like that. So m of t can be represented as m of t equal to a naught plus a1 cos 2 pi f naught t plus a2 sin a2 cos 2 pi f naught t plus b1 sin 2 pi f naught t plus b2 sin 2 pi f naught t, and so on. So here we will write this one as m of t equal to a naught plus sigma n equal to 1 to infinity an cos n omega naught t plus bn sin n omega naught t. Okay, so this is equation number 2, and from this we can write the expressions for a naught, an, and bn. A naught is nothing but amplitude of DC component. An is amplitudes of corresponding cosine components, and bn's are amplitudes of corresponding sine components. So here we have some three formulas are there for a naught, an, and bn. A naught is defined as a naught equal to 1 by t naught integral t naught to t naught plus t naught m of t dt. An equal to 2 by t naught integral t naught to t naught plus t naught m of t into cos n omega naught t dt. And bn equal to 2 by t naught integral t naught to t naught plus t naught m of t sin n omega naught t dt. So this trigonometric Fourier series expansion of m of t can be expressed by the equation m of t equal to a naught plus sigma n equal to 1 to infinity an cos n omega naught t plus bn sin n omega naught t. For our convenience, it can be converted into more compact form, that is m of t equal to s naught plus sigma n equal to 1 to infinity Sn cos n omega naught t minus phi n, where S naught is nothing but a naught, and phi n equal Sn is square root of an square plus bn square, and phi n is minus tan inverse bn by an. For all trigonometric form of Fourier series, we will find out all these parameters S naught, Sn, and phi n for all problems, and this is the proof. So here arbitrary signal m of t is taken as m of t equal to an cos n omega naught t plus bn sin n omega naught t. Okay, so divide this this RHS side with the square root of an square plus bn square. So an by square root of an square plus bn square into cos n omega naught t plus bn by square root of an square plus bn square into sin n omega naught t into divide and multiply square root of an square plus bn square. So uh, there is a triangle, right angle triangle will form with the sides an, bn, and this is a hypotenuse square root of n square plus bn square with the phase angle phi n. Okay, so this equation 3 can be represented as cos phi n into cos n omega naught t plus sin phi n into sin n omega naught t into square root of an square plus bn square. Okay, and m of t equal to this is in the form of cos a cos b plus sin a sin b, that is nothing but cos a minus b. Okay, here cos n omega naught t minus phi n into Sn, where Sn is square root of an square plus bn square, and phi n equal to minus tan inverse bn by an, right? Okay. Okay, so this indicates that time domain signal m of t can be represented in frequency domain by its amplitude spectrum and phase spectrum. And we'll do some problems also. We have done some problems based on these formulas, right? First of all, for any given problem, we have to write the fundamental time period first. Fundamental time period, that is T naught. T naught will be written from the given diagram. Okay, so T naught will be T naught is first of all we have to notify the T naught. After that F naught will be notified. After that omega naught will be notified. Omega naught equal to 2 pi F naught. Okay, so and after that based on this fundamental time period we will write the formulas. Okay, we will write the expression for m of t also m of t equal to e power minus t for 0 is less than t is less than 1. Okay, okay, so from this we have to find out the a naught, an, and bn. Okay, here I already told you that we have to remember the integration formulas here. Okay, so by simply recollecting the integration formulas, we can use those formulas at here. Okay, so by knowing those formulas we can solve these problems. Okay, we can solve these problems, right? We can solve these problems, right? Like this we have done so many problems. After that we will write mod sn equal to square root of an square plus bn square, and then phi n equal to minus tan inverse bn by an, right? So then we will write the, or we will draw amplitude spectrum as well as phase spectrum. Amplitude spectrum as well as phase spectrum. Amplitude spectrum is drawn between amplitude versus frequency, and phase spectrum will be drawn between phase angle versus frequency. Like that, we had done several number of problems. And see here in this problem, this is an even signal. This is an even signal. Even signal means it has to satisfy the condition m of t equal to m of minus t. For this type of problems, we don't have sine terms. Only we have cosine terms, right? We don't have any bn term. Okay, only we have to find out an term only. Bn term is zero for this one. Okay, since it is an even signal, it contains only cosine terms, not sine terms. That's why bn becomes 0. So we'll find out an here. So with the help of a naught and an, we'll write the m of t, arbitrary function m of t, and then it will be converted into its our convenient form, compact form, that is m of t in terms of s naught and s of t. So Sn is equal to square root of an square plus bn square. Here bn is 0, only we have square root of an square, and s naught is nothing but a naught. So that will be calculated. So for this type of problems, we don't have any phase spectrum. Why? Because Bn term will be 0. Bn by An, that is minus tan inverse Bn by An minus tan inverse 0. So that is 0. Okay, we don't have any phase spectrum for this type of problems. And this is half wave rectifier. Okay. So here, uh, accidentally we will get Bn value as 0 here. That's why here also we don't have any phase spectrum. And this type of problems are also Bn is 0. Okay. Like this, we had done so many problems. Next, exponential form of Fourier series. So exponential form of Fourier series, here the signal is represented as a linear combination of basic signals. So here the basic signals are sine and cosine cosine signals, right? So here these are sine and cosine components, right? So here the signal exponential Fourier series is represented by m of t equal sigma n equal to minus infinity to infinity cn into e power plus j in omega naught t. Here cn is nothing but exponential Fourier quotient, that is sigma 1 by t naught into integral t naught to t naught plus t naught m of t into e power minus j n omega naught t dt for n is not equal to 0. If n is 0, it will become c naught. That is 1 by t naught integral t naught to t naught plus t naught m of t dt for n equal to 0 only. So for this exponential Fourier series, we will find out c naught and cn values, right? C naught and cn values. Then find the then this is also an even type of signal, right? So for this problem also we will find out c naught and cn. Okay, c naught and cn, and look and find out mod cn, that is 1 by 2 pi, and there is no imaginary term here, so that's why there is no phase spectrum. So imaginary term is there already. Cn equal minus j by 2 pi n. So only imaginary term is there. So imaginary term by real term minus tan inverse imaginary term by real term. Okay. After that, we will find out the magnitude spectrum as well as phase spectrum. Okay. Like this, we will do the problems. Okay. This is also, we have magnitude and phase spectrums. For this also we have magnitude and phase spectrums. Next, we'll discuss about the Dirichlet conditions. Dirichlet conditions, these are very important. We have three Dirichlet conditions. The for any period x of t must be integrable. Okay. Next, we have finite number of maximas and minimas. Next, we have finite number of discontinuities over the finite interval, right? Next, we will derive the relation between trigonometric and exponential Fourier series. Okay, so let us take the trigonometric Fourier series, arbitrary function trigonometric Fourier series. Okay, so here e power j n omega naught is represented as e power plus or minus j n omega naught, that is cos omega naught plus j sin omega naught. Okay, so by extracting this, so and compare by extracting this and compare with this trigonometric form, so we will get the relation a naught equal to c naught and an equal to cn plus c minus n, bn equal to j into cn minus c minus n. By rearranging the above equation, we will get the expressions for exponential Fourier quotients in terms of trigonometric Fourier quotients as c naught equal to a naught, cn equal to half of an minus j bn, and c minus n equal to half of an plus j bn, right? So next we will derive the representation of periodic function by the Fourier series over the entire interval. So far we discussed about during the finite interval only, we can say that Fourier series is equal, but over the entire interval, we can say that Fourier series is equal. So we have to derive the right hand side. Right hand side should be proved as periodic. If it was proved as periodic, then we can say that it is Fourier series is equal over the entire 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 period. Okay, so phi of t equal to phi of t plus t. Okay, so this is the periodic signal and its Fourier transform. Next, we derived the we explain the properties of Fourier series. These are also very important properties: linearity, time shifting, frequent shifting, time scaling, time differentiation, convolution, multi multiplication, and symmetry property. Okay, these are defined. These are very important. Next, complex Fourier spectrum we derived. Okay, this is complex Fourier spectrum. Okay, next one is mm, Fourier transforms. Okay, here we are representing these Fourier transforms as linear combination of harmonically related complex exponentials. Here, the periodic signal and non-periodic signal, we will relate these two periodic and non-periodic signals. So, by applying limit t naught tends to infinity, periodic signal limit t naught tends to infinity of the periodic signal is equal to the non-periodic signal. That is limit t naught tends to infinity x p of t is equal to x of t. So we derived this one. Okay. After that, we will see the relation between t naught. As t naught becomes greater and greater, larger and larger, f naught becomes smaller and smaller, and omega naught will become smaller and smaller, so that we will get the denser frequency spectrum. Okay, as we are increasing the t naught. Okay, so here we explained the relation between these two x of t and x of omega. So these two are called Fourier transform pair. Fourier transform pair. X of t and x of omega are called Fourier transform pair. Okay, so Fourier transform of x of t is x of omega, and inverse Fourier transform of x of omega is x of t. That's why these two are called Fourier transform pair. Fourier transform pair. Next, here also we have the Dirichlet conditions. So here also same, the Dirichlet conditions are same for any finite interval. X of t must be integrable, and here we have finite number of maximas and minimas, finite number of maximas and minimas within any finite interval. And next one is finite number. We have finite number of discontinuities within any finite interval. Furthermore, each of these discontinuities must be finite. Okay. So next, we also done some problems on Fourier transform. So what is the formula for finding the Fourier transform of x of t? Fourier transform of x of t is equal to integral minus infinity to infinity x of t into e power minus j omega t dt. Right? So like this, in this by using this formula, we have done so many problems. Okay. So after that, after finding the Fourier transform, we have to draw the magnitude and phase spectrums here also. Okay, so magnitude spectrum will drawn between magnitude versus frequency, and phase spectrum will drawn between phase angle versus frequency, right? Phase angle versus frequency, like this. We have done so many problems here. Okay, first of all, we have to write the equation from the given diagram. We have to write the equation from the given diagram. Okay, so after that, we will substitute this that formula. Okay, right, like this. We draw the magnitude and phase spectrums. So for this also magnitude spectrum. For this also we have a magnitude spectrum. This is signum function. So signum function, how the signum function is defined? Signum of t is equal to -1 for t is less than 0. It is 0 for t is equal to 0, and it is 1 for t is greater than 0. Or we can define signum of t in terms of a unit step functions as it is u of t minus u of minus t. U of t is unit step function. U of u of minus t is its mirror image. So it will be reverted, inverted version of its mirror image. So by adding these two, we will get the signum function. Okay, so 2 by j omega will get the expression, and after that we will draw the magnitude and phase spectrums. Okay, like this impulse function. For impulse function also we'll draw the magnitude spectrum. So for unit step function also, uh, uh, it will be uh, it will be framed as a sum of signum function, half of the signum function, and constant function, half constant function. By adding these two, we will get the unit step function, and its magnitude spectrum is like this. Okay. Next, here also we have the properties of Fourier transforms, linearity property, time shifting property, frequency shifting property, differentiation property, integration property, scaling property, duality property, convolution property, and last one is Parsells theorem. So we derived the expressions for all these properties here. Okay, properties here. Okay, after that we'll derive the Parsells theorem. Parseval's theorem for energy signals also, that is E equal to 1 by 2 by integral minus infinity to infinity x of omega into x of minus omega d omega. Okay, so for complex here x of omega and x of omega Fourier transforms are if for real signal x of t, the Fourier transform x of omega and x of minus omega are complex conjugates, then x of minus omega will become x star of omega. So that we can write like this: x of omega into x of minus omega is equal to x of omega into x star of omega. That is nothing but mod x of omega square. So E can be represented as E equal to 1 by 2 by integral minus infinity to infinity x of omega square d omega, that is minus infinity to infinity x of omega square into df. Why? Because d omega can be substituted as 2 pi f omega equal to 2 pi f. So 2 pi gets cancelled. This will become df. Next, we derived the Fourier transform of periodic function. Fourier transform periodic function. Actually, Fourier series is for periodic functions. Fourier transform is for non-periodic functions. But here we derived Fourier transform may be used as a universal mathematical tool to analyze both periodic and non-periodic function. Here we see the Fourier series of periodic function, that is x of t equal sigma n is minus infinity infinity cn into e power minus j omega naught t n. That is equation number 1. After that we will take the Fourier transform for that one. So by using the frequency shifting theorem, we can derive Fourier transform of x of t equal to 2 pi into sigma n is minus infinity to infinity cn into delta of omega minus n omega naught. Okay, here the Fourier transform of any periodic function consists of a train of equally spaced impulses, that is omega minus n omega naught, and these impulses are located at the harmonic frequencies of the signal, and the strength of area of each impulse is given by 2 pi into cn, right? Okay, after that we have done some problems on inverse Fourier transform. Inverse Fourier transform of x of omega. Okay, delta of omega. So here also for a we draw the magnitude spectrums, and we also find the Fourier transform of delta of omega minus omega naught, that is mm, uh, inverse Fourier transform of delta of omega minus omega naught will become 1 by 2 pi into e power j omega naught t, or Fourier transform of 1 by 2 pi into e power j omega naught t is delta of omega minus omega naught, or cross multiplication e power j omega t naught, e power Fourier transform of e power j omega t naught is 2 pi into delta of omega minus omega naught. Similarly, e power minus j omega naught t Fourier transform of this one is 2 pi into delta of omega plus omega naught. After that, Euler's identity. By using Euler's identity, we will write e power j theta as cos theta plus j sin theta, and e power minus j theta is cos theta minus j sin theta. By adding these two, we will get the expression for cos theta, that is e power j theta plus e power minus j theta by 2. By subtracting the uh, e power minus j theta expression from e power j theta expression, we will get the expression for sin theta. Okay, so the Fourier transform of cos omega naught is pi into delta of omega minus omega naught plus delta of omega plus omega naught. Then we will see the Fourier transform of the rectangular pulse also. Okay, so this is about the second unit. This is about the Fourier series and Fourier transforms. Fourier series and Fourier transforms. Right? Okay. So I will give the material also. I will post the material in your group. So if you have, please thoroughly follow the concepts. If you have any doubts, you can contact me. Okay. So for today I will end the session. Tomorrow we will see the remaining. Tomorrow we will see the we may start the next unit. Okay, thank you.